Good morning, everyone. So my name is Marton Tamas, and I'm the lead of developer support at PowerVR. And today I would like to talk to you about how we optimize and profile games on PowerVR in the office, and to really give you like a showcase of how we do things. So let's get started. But before that, if you have any questions during the presentation, you can go to sli.do and use the code U724 to get into like a chat system, and you can ask your questions there. I'll do my best to answer them at the end of the presentation. All right, so today's agenda, I'll first talk about imagination and PowerVR, just to introduce you, those of you to it a bit that don't know it. And then we'll see how PowerVR is different to other GPU architectures. And then I'll show you how to do top-down profiling using PVRTune. Then we'll do some live demos, and finally we'll have a Q&A session in the end. So PowerVR is the brand of GPUs that Imagination Technologies produces, which is a global technology leader for graphics, multimedia, communications, and AI IP. We are proud to say that last year we have shipped 1.2 billion units, which is a huge number for us. And these GPUs have quite a wide range of performance, all the way from low end, which is focused on like fill rate density and performance density, to high end, which is focused on power efficiency and performance density. So as you can see, we have quite a number of devices out there. I think in 2018 alone, we had like 70-something phones released, and these are quite big names, such as Huawei, Honor, Oppo, Vivo, Xiaomi, Meizu, Realme, Nokia, and Sony. Most of the mobile phones that you can see here are mid-range to low-end phones, but as you can see, the performance range is quite wide. So on the low end, we have GPUs that are mostly only capable of 720p graphics, and on the high end, we have beasts capable of 1080p graphics. All of our GPUs support Vulkan. Fully, depending on the driver, you might get better quality with later phones. But obviously, it's best to work with us if you're releasing your Vulkan title, to make sure that we can give you the workarounds if necessary, or the fixes if necessary. So around the end of 2019, around 2019 summer, we expect Helio P90, the new SoC, come out, and that is capable of really good 1080p performance, and some really good mid-range devices. So what is PowerVR? So PowerVR Developer Technology Engineering team is PowerVR's community-facing team. We provide a number of free services, such as application support and analysis, which could be very useful to you. You can contact us through our forums and ticketing system, and there you can interact with others as well. We also provide some tools that you can use, such as the profile I'm going to show you today, and we also have some debuggers and some other tools as well. We provide a wide range of documentation, all the way from architecture to how to optimize for our ALU, and how to use our tools, and etc. We also do training and workshops, both in person and over Skype, so that's a good opportunity if you don't know much about PowerVR, to contact us, and so we can arrange something. So now let's talk about graphics architectures. So first, let's go through the traditional graphics architectures. So let's start with immediate mode rendering. So immediate mode rendering works by essentially taking a primitive, such as a triangle, sending it through the entire graphics pipeline without doing anything clever, and then rasterizing it and putting it on screen. So this wastes a lot of ALU and bandwidth, and it's not really efficient, and usually you need to utilize large caches to sort of alleviate this or do other tricks. To combat this, especially on mobile, tile-based rendering was introduced. So tile-based rendering, as you can see on the graph, is a bit more clever. So after the fixed function vertex stages, it does some tiling, which means that now we can process the image in little bits of tiles. And this allows us to utilize an on-chip buffer that we can use to accelerate certain operations, such as depth testing and alpha blending. And this means our system now is a lot less bandwidth hungry. It does come with some overhead, so we do need to write out the tile geometry data to system memory, but we can do some clever tricks to help with that. So how is PowerVR different? So PowerVR has a unique smart rendering architecture called tile-based deferred rendering. So on mobile, it's very important to be tile-based, as alpha banding and depth testing are quite bandwidth-intensive operations. And resolutions have been going up from all the way from like 720p to now 4K, and maybe even beyond, coming further next year. And tile-based solved this by dividing the image up into tiles, like I said before, and this allows us to use fast on-chip buffers. So PowerVR is still tile-based. We do have that on-chip buffers. That helps us a lot. But we are also deferred. So what does that mean? So deferred means that we postpone all shading and texturing operations until all opaque objects have been tested for visibility. And to do that, we've introduced a new block called hidden surface removal, which essentially calls all occluded pixels using predetermined visibility accelerated by the on-chip depth buffer. So this results essentially in zero overdraw. As you can see, the top image is how the final rendered image would look like. On the right-hand side for you, you can see how it looks like for traditional rendering architectures. And on the left-hand side, no, sorry, the other way around. So left-hand side for you, and on the right-hand side for you, you got the PowerVR version, which results in not really much overdraw at all with the opaque bits, and as you can see, only the GUI adds some overdraw. So, the advantages is that we can do fast blending, fast depth testing. We don't need to resort to tricks such as depth pre-pass and geometry sorting to reduce our overdraw. And we save a lot of ALU and bandwidth and TPU performance. And post-fragment operations as well, and varying interpolation by utilizing this deferred architecture. So all of this makes PowerVR the most efficient rendering architecture today. But this wouldn't be that good today, wouldn't it? So we need some more special sauce to spice it up. So PowerVR employs a number of compression techniques to further help with bandwidth usage. So first, we introduced frame buffer compression, which has two kinds. One of them is lossless, so that basically means that your compression ratio will depend on the content that you're rendering. So if you're rendering just simple noise, then your compression ratio will be horrible. You'll be essentially just as if you didn't have any compression at all. And if you're rendering just a solid color, your compression ratio will be really, really good. You'll be down to, I don't know, a couple of maybe kilobytes or something instead of megabytes of frame buffer size. And then we have lossy, which is different in a sense that it guarantees a 50% compression ratio. And obviously it's a lossy compression, so you don't get back the same image. However, the quality is comparable to lossless because it is a perceptually lossless algorithm. So the users won't really know that you are doing something funny there. Then we have geometry compression, which basically helps with the overhead of tiling, having to write out all that memory to system memory. And we also have, but that happens, transparently and behind your back, so you don't really need to worry about it that much. We also have texture compression that you can utilize by using our tool, PVRText tool. You can compress your textures with. We support a number of different formats that you can see there, and essentially that will help your your texturing and your bandwidth usage when you're running your application. So our current architecture, to be exact, is PowerVR Rogue. That is on the market and is in the mobile phones that you've seen, and it's also in the upcoming phone as well. So it is optimized for data parallel workloads running on many threads. It is a single instruction, multiple data architecture. That means that multiple threads execute the same instruction but it is scalar, so one thread operates on one piece of data at a time. And that also means that there's no need for vectorization, so the compiler takes care of it for you. Our wavefronts are currently 16 wide, which means you need to pay attention to fill that with stuff to do. So when you're doing your Bloom kernels and whatnot, make sure you include some math in there, so they're not just sitting there lazy doing nothing. Our cores are, our shader cores are unified, which means you can run vertex, pixel, and compute workloads in parallel, and these are automatically scheduled. So unless you're synchronizing them, you really get the most overlap possible. And this has been true, I think, way before async compute was introduced. So if you're not synchronizing things, they just run in parallel and overlap. So the other thing that we have is the half precision ALU pipeline, which has doubled the performance of the full precision one. So please use medium P wherever possible, because it essentially gives you free performance that's available and for you to utilize. It is quite a unique ALU architecture because it implements the sum of products instruction that you can see on the slide. You do need to be aware of that. So please, if you're optimizing for PowerVR, then make sure that you design your algorithms and your math so that it looks something like that all the time. Now let's talk about PVRTune, our profiling tool. So PVRTune is a multi-platform GUI-based visual profiler that provides real-time hardware and software performance counters along with API data to help developers pinpoint exactly where a bottleneck lies. As you can see, we support a number of different platforms such as Windows, Linux, and macOS, and also a vast amount of data such as GPU counters, CPU performance data, driver information, and various API data from Vulkan and OpenGL as well. When designing PVRTune, the key focus for us was user experience. So therefore, we introduced a feature called the one-click setup feature. So this essentially allows you to set up your profiling session with just one click. All you need to do is just plug in your device or connect through ADB Wi-Fi and click the button in the GUI, and that will PVRTune will automatically deploy the server application onto the device, and data will begin to be transmitted. Deployment is currently supported on Linux and Android. But on Android, for unrooted devices, you do need to use a different application called PVR Hub for now, but we plan to hide that in the future, so it will become a truly one-click setup regardless of whether you have a rooted device or not. So then you can just use the one-click setup in all the retail devices, and that will be very nice. In PVRTune, we represent workloads by timing blocks. Each block represents some amount of work, usually tied to processing a frame buffer. So if I could just move it cursor here, so as you can see, this would be one frame buffer that we are processing, and the tiler tasks here are corresponding. And we color them using the bottom color that says which frame buffer this belongs to. The middle color is essentially which frame, and the top one is which process. So basically, the bigger the timing block, the longer it takes to process it. We arrange these timing blocks by categorizing them for each resource. So as you can see, we have a renderer timeline, we have a tiler timeline. So this is renderer one, this is the tiler one, and we also have some compute here. Finally, we overlay counter data in the form of these graphs to kind of visualize how hardware counters change over time. So profiling can be done in many ways, and I'm sure you've seen a couple of them already. But due to the complexity of mobile games and SoCs, we need to identify issues in a sort of top-down fashion. So we always start with, my app is slow, or maybe I'm not reaching my 60 FPS goal that I set out, or maybe you just want to improve your power efficiency and your thermals because your users were complaining or something like that. So we start from that point, and then we need to identify which component is the bottleneck. So the application could be the CPU or GPU bound, and I'm sure in the future we might see some AI bound applications as well. So if it's GPU bound, it further can be broken down to it's either vertex bound or pixel bound, or we could see compute bound as well, but that's more rare on mobile. If it's CPU bound, it could be either API bound or the application is doing some other work, which could be, the application is just busy doing physics or I don't know, whatever you guys are doing. So when we need to identify bottlenecks, we need to start from the most expensive one, so that's the middle one, marked as first, all the way to the least expensive one to get the most return for our time investment. After we profile the app, we need to identify the problem, and then we need to optimize the app. And then finally, we need to test it again and verify our results. And all this kind of forms a cycle that we need to follow until we reach our goals. And you need to be careful to kind of follow this and never forget that you need to reprofile again after you optimize your application, because you might run into a different kind of problem or something like that we'll later see. One pro tip though is if you're profiling GPU bound applications, then make sure your clock speeds are fixed so that your results are consistent. So how do we know if our app is CPU or GPU bound? So in PVRTune we have a tool called the monitor. So that basically shows you a quick glance over what your application is doing. So in this example, we can see that this application is quite silo bound, so you have a lot of vertex workload, and you can also see that one of the CPU cores is just fully maxed out. So if we're gonna deal with the tiler issue, then we also need to probably deal with the CPU side as well, because then it will become CPU bound. So let's have a closer look. So I'll show you 4 examples of exactly how we do profiling in the office using PVRTune. So the first example, I just want to quickly highlight that you can see it's quite tiler bound because the bottom bit is fully saturated, and there could be many possible causes. So it could be that your application submits too many vertices or tiny triangles that just make up a lot of vertices again, or it could be that your vertex attributes are cache inefficient, or it could be that your vertex shaders are simply too expensive. So in this example, as you can see, well, I'll show you live later on, but we submit a lot of triangles. And the other thing to notice is that if we plot the triangle submit per frame graph, we can see that the workload changes as we process different parts of the screen. So this really shows how our GPU kind of works. So you don't get like a constant load or a load that ramps up and then goes down, but it's rather it changes rapidly as we process different tiles and the workload changes. So now let me go through the first example. I think that's number 4. Yeah, it's this one. So if you look at the monitor widget, we can see that, like I said, the tiler is quite active and one of the CPU cores is maxed out. So we need to look at both. So to start, we need to highlight a section. So let me just do that. And then we need to look at our counters here. I can't quite see them, but there we go. So, so one of the counters that we might be interested in is the triangles input per frame. So as you can see, the application in this selected area submits 223,000 triangles. That's quite a bit. That's like 700,000 vertices. On mobile, that's quite a bit of a workload. So if we plot that, we can see that it changes quite a bit, and then there's actually a spike over there. So that could be a bottleneck that we need to deal with. And also, the other counter that we need to look at is vertices per triangle. As you can see, that's constant 3.0, so that basically means that the application's triangles don't share the vertices, and that will cause cache inefficiencies. So in order to overcome this problem, we can do a number of different things. We can call more triangles, or we can try to reduce our mesh complexity if possible, or we can use a tool called Mesh Optimizer that allows us to increase vertex sharing and thereby increase our cache efficiency. We can also consider interleaving our attributes if we have not done that already. That will also help with the inefficiencies in this example. So in the second example, oh, it doesn't go back. There we go. So in the second example, I'll show you an application that's pixel bound. And again, there could be a number of different causes. So on PowerVR, it could be that you're doing something funny and the hidden surface removal bit is not very efficient. So that basically means that it would be like around 0% or close to that mark. So usually if we pair that with the overdraw metric, we can see that maybe your application is submitting too many alpha blended primitives, and that causes our hidden surface removal to not be able to remove your occluded pixels. Your application might also be doing some depth load stores. That essentially means that you are storing a depth buffer into system memory that you should not. So normally what would happen is we just do our depth testing on chip, and then we discard that memory. We don't need it. We are not writing it out ever into system memory, and that's very bandwidth efficient, but if you're storing it in system memory, such as for shadow mapping or things like that, that will cost you bandwidth, and that will show in PVRTune. It also could be that your shaders are simply too expensive. So we have various tools for that, or you're consuming too many registers, or maybe your shadow map is just too high resolution. Or maybe you're taking too many texture samples and you need to consider using something, a different filter or less samples or something like that. Or it also could be that your samples are spatially incoherent, so that will cause some cache inefficiencies, especially in mobile because we don't have that large caches. So let me go to the second example. I believe this is the one, yeah. So as you can see here in the monitor widget, we can immediately see that this application is render bound, so we have a lot of pixel workload going on. So, and as you can see, the other resources are kind of not really used, so the CPU is mostly idle, the tiler is mostly idle. So let's have a look why this application is pixel bound. So there we go. So if you look at AGSR efficiency and plot that for a second, and zoom in a bit. Is this the correct example? That's number 4, sorry. I need number 2. This is number 2. Alright, so same situation, we're still render bound, don't worry. So if we plot AGSR efficiency, you can see that we have quite a number of dips here. So here efficiency goes down to like 15, 18%. And then it goes back to normal, which is about like 50%. And if we plot overdraw as well, we can see that wherever the AGSR efficiency dips, we have an overdraw spike. So we need to look into our overdraw issues using PVR trace or something like that. If you look at that load store, and if I just quickly highlight the section for you, you can see that it's not too bad, it's 11%. But we do have quite a bit of spiking going on. So that basically means that some bits of the renderer pipeline that your application uses writes out depth to system memory. And you maybe need to look into it, whether that's intentional or not. So the next counter we should look at is processing load pixel. So as you can see here, some parts of the application are quite early bound because our shader cores are almost working 100% of the time, but other parts are not that much so. But this shows that if we were to optimize the shaders in this regard, we could win quite a bit here. So that keep that in mind, because if you're going to optimize this application, then later on it might come handy. So the next one is register overload. That looks quite good most of the time, but there are some spikes. So I'd recommend looking into it maybe towards the end of your optimization session. And then what we really need to focus on, and PVRTune actually highlights it in red, is texturing active. So if I activate that, you can immediately see that this application is just hammering our texture processing unit all the time. And the other counter that is interesting is texture overload. That basically means that the application is spending like 30% or more of its time just waiting on texture samples to arrive. So that is really, really bad when you would like your processing to be fluent and efficient. You can't be spending time just waiting for texture samples to arrive. So in order to overcome these issues, you can do a number of things. So like I said, you need to look into your overdraw. You need to look into why you're outputting that. Is that intentional? You need to look into your shaders to figure out why they are so expensive in some parts of your application. You need to look into your register usage, figure out which render task is inefficient and optimize it. And finally, you really need to look into your texturing activities and really consider using texture compression, consider using lower resolution textures, consider using less samples if you're doing some kind of kernel, consider using less complex filters, such as instead of anisotropic filtering, you could go down to billionaire filtering, or well, whatever you prefer, or trillionaire filtering. I think on mobile a lot of things work. But you definitely don't need 16x anisotropic when you're only rendering to a 6-inch screen, right? So, and also we need to look into your texture cache efficiency, whether you can optimize your kernel so that you're more spatially coherent there. So after you've done all these things, obviously you need to go back and verify your results. So one of the things to know about this application is we can see that the renderer is quite busy, but there are a couple of gaps, which is interesting because ideally we wouldn't have any gaps. We'd just be rendering all the time, or if we would like to do compute, then we'd be doing compute all the time. So if we zoom in, we can see that this gap is actually quite significant, 4 milliseconds right there, right? So why is that there? Why can we, push the renderer here? Well, it's probably because the application is doing some kind of synchronization there that basically prevents all the subsequent render workload to be moved to the left. And in order to have a look at why that happens, we need to use synchronization objects. So synchronization objects are basically our method of scheduling GPU work on the device. So our firmware processor will use those to kind of schedule them. So if they are not signaled, the GPU can't really schedule your task. So then this happens, you need to wait until they become signaled. So let me just quickly highlight this single render task, and then we can select the synchronization object. If I can click it, there we go. And then let me enable the sync objects here. And then, as you can see, you can observe 2 things. So there are 2 sync objects that this render task is waiting on. One of them here coincides with the end of the compute workload. So that basically means that this render task is waiting on the compute workload to finish. And the other one is signaled here. So that means that the other task that it's waiting on is obviously the previous render task. So this signals to us that, we have a synchronization issue between compute and render workload, and we need to look into it, whether that's intentional, so whether the render does some subsequent processing, or maybe we do some barriers that we shouldn't be doing, or maybe we have a driver bug in which case you need to contact us and tell us that I see no reason why this shouldn't be overlapping. Can you please have a look into it? So let's move on. There we go. So this is what essentially I've been showing you. So this is how sync object is made up. So as you can see, the green bit is when it can be scheduled. The red bit is when it's waiting for some resource or some computations happen. The red bars when the firmware checks whether something happened and whether it can turn it to green, but the check fails, so it still needs to stay red. When it's colored, obviously that means that the task is running, and when it's gray, that means the firmware is doing some updates. So there might be cases where your shaders are just simply expensive. So how can you really profile that, especially on a deferred architecture? So as you could see that we tie our GPU workload to frame buffers, processing of frame buffers, and not like individual draw calls. So if you look in the example, if you click one of the render tasks, and you look in the properties window, we list all the shaders associated to that render task. So you can go into each shader, and we provide some advanced statistics and also per line cycle count. So how do we do that? We have a accurate offline per hardware compiler that is built into PVRTune that will give you accurate statistics for the specific hardware that you're running on. So that allows us to not have to deal with overhead on the device, but we rather can do it cleverly on your PC. You might run into some situations where you've done your due diligence and the application is quite optimized, and there's no really clear way of improving performance without sacrificing visual quality. So in these situations, we recommend looking into whether you can balance your workload. On PowerVR, there could be a number of different ways that you can do that. So essentially what you're looking to do is when one resource is fully utilized, you're looking to sort of shift workload to another resource in a clever way, and therefore you can free up some of that and you can achieve faster performance. So on PowerVR, we have a number of different GPU resources, such as the ELU, texturing, the image synthesis processor, which is basically the visibility testing unit, and renderer, tile, and compute. Oh, sorry. So just to give you an example how to trade resources one for another. So in the previous example, we saw that this app was quite texturing limited. So what you can do in this case is you can implement some procedural texturing and use your ELU resources, which were sometimes quite idle, and you can actually shift your texturing workload to ELU that way. Or if it were the other way around, you're just really ELU limited, you can pre-calculate your equations into lookup textures and use texturing. Or there could be cases where you're both ELU and texturing limited and you just can't really do anything, such as when you're rendering foliage and you are using alpha testing. So in that case, you can actually run a depth pre-pass, not in the traditional sense, because you wouldn't be writing out depth buffers to system memory, but you're essentially just doing like a preparation of the depth buffer on chip. And then you use depth testing to call all the occluded pixels, so that way you can utilize the hidden surface removal capabilities of our hardware again. Because with alpha testing, you need to execute the shader in order to find out whether that pixel contributes or not. So that introduces a little overhead there, so you can optimize it that way. That would mean that your very expensive foliage can now be quite cheap actually, because you've done a cheap pre-pass with really cheap shaders and some maybe simplified geometry or something like that, and then you essentially have zero draw again. So foliage is kind of cheap that way. This can improve performance significantly, and it's quite a neat trick. So in some cases, for example, when you're doing like a bloom filter, right, you have a number of different passes that you have to do, such as downsampling and then upsampling and blurring different levels of the bloom chain. So you might end up having small render tasks that look like this. So as you can see here, the middle bit, which is highlighted by a black bar, is when the actual shader processing occurs. And all the rest is simply filling up the pipeline and then draining it. So this means that the overhead for processing that geometry and those pixels is quite large compared to the actual workload that you're doing. So that means that you can be pipeline overhead bound. So possible causes for this could include when you're filling the pipeline, you could be doing too much vertex data fetch or rasterization, interpolation, and visibility testing. And when draining the pipeline, you could be running into having to write out all your pixels, all your vertex data, and the fixed function phases that you have. And to reduce this overhead, we can't really reduce our render workload, but what we should rather be looking at is whether we can merge it with something else so that the overhead becomes smaller and essentially disappear into or overlap whenever the shader cores are doing something. There could be some cases when your application is CPU bound, and there are two ways it can be CPU bound. One of them is you're bothering us too much and you're touching the driver too much, so too many OpenGL calls, draw calls, whatever. And the other way is you're doing something yourself. And when you're API bound, when you're working with the driver too much, there could be a number of causes, such as you're submitting too many draw calls, or you run into some ghosting or data transfers, or you're doing shader compilation in the middle of the frame, or you could run into a driver bug. So let me show you the last example. So in this case, as you can see, we are quite CPU bound, so a number of CPU cores are quite busy. And if you look at the client stream data that you need to enable in order to see the API data, you can see here that we have 24 millisecond buffer uploads. So that is quite a problem, and you need to look into whether it's simply you're submitting too much data, so you write a memcopy that copies the same amount of data and see whether that takes longer or not, or a shorter period of time, or whether the driver is doing some kind of transformation on your data, in which case you need to kind of work with us to figure out why that happens. And let me show you one last example. This one. So this will basically tell you how to notice ghosting in your application. So if you scroll down to the per PID counters, you can see we have a new counter called GLES device memory copy, and that will basically show you spikes in the OpenGLES driver memory copies whenever ghosting happens. So that's a pretty neat way to notice that. In Vulkan, of course, you control your memory, and it's all up to you. However, the kernel might still do some allocations, and we also have a counter for that called the host kernel memory usage. They can track to see whether the driver is doing something funny behind your back. So I had 5 minutes, right? So I think we should move on to the questions. So thank you very much for your attention. And if you want to continue learning, you can follow that URL. If you would like to be hired by us or apply for a job, then we also have that link over there. And now we'll move on to some questions. And I do have some T-shirts if you want, so you can come up to me at the end of the presentation, and I can give you some swag. All right, thank you.
Thank you. We have 5 minutes. Do you have some questions? Do you want to ask for something? Consult? We have now time.
Hi, you said that 75,000 vertices was too much for mobile CPU. So how many you prefer is optimal size or number of verticals?
Depends on the GPU. As you could see, we had 1x performance to 3x performance to even more and then beyond. So it depends on the capabilities of the GPU.
But on the PVR, the latest one, the most powerful?
I would say on that particular core, first of all, you would need to increase your cache efficiency and then see what your performance looks like, and then see how much primitives or vertices you can fit into your 60 FPS budget or whatever the budget you have. So I think there it was about 15, 16 milliseconds of that, just that big vertex task. So, but I think that would go down to like maybe 10 milliseconds or something after you optimize your cache efficiency or your interleaver attributes. And then maybe you can just live with that, or maybe you need to do some further reduction.
Okay, thanks.
Thank you. More question? I haven't. So thank you.
Thank you very much. Let me have a look at the online questions if you have any.
Maybe it was the question.
I can't see any of them, so thank you very much for your attention.
Thank you.